So we are now in projectile motion, a very good example of a two-dimensional motion, also called translational motion, wherein we have the motion of the object for its horizontal and vertical components. In chapter 2, we talk about rectilinear motion. This type of motion is more of a straight line, and we've analyzed it, talking about its displacement, velocity of the object, and its acceleration, which also include a free-falling object. In two-dimensional motion, we are going to examine objects that are moving in a curved path, also referred to as a parabolic path. So in two-dimensional motion, objects that are in near Earth's surface, such as a basketball thrown, a bouncing ball, showing a parabolic path. So these are the ones that we are going to examine. These are examples of projectiles. So although air resistance is an important factor in analyzing motion, we are going to ignore its effect in our analysis of projectile motion with a parabolic path. So the main concern that we have here, our main concern would be the projectile motion. The object or the system we're observing have already been projected. So let me write it down. Our main concern would be after the object has been projected. Another thing is before it lands or is caught. When it is moving freely under the action of G alone. So we are not in the process of knowing how it was thrown, how good you were, and we are not going to look into that. So these are the things that we are going to look into. So projectile motion have two types. This one is called objects, first type, thrown horizontally. So in objects thrown horizontally, we consider velocities of the object. So we have the horizontal initial velocity and also the horizontal vertical initial velocity. In this first type of projectile motion, the initial horizontal velocity is 0, and the vertical is 0. The initial horizontal velocity is equal to the change, which is equal to v cosine theta. In this case also, we have to take note that the object is moving at a constant horizontal velocity, which means acceleration is, yes, is 0. So we could see here, we can analyze from this picture that an object thrown horizontally, we could analyze that there are components. You have the vertical components, so the initial vertical velocity there is 0, and the only thing that affects it is the acceleration due to g, which is downward. And we know that before it hits the ground, its final velocity would be different. Now, in a horizontal component of the velocity, we would notice that the vector motion doesn't change and gives us an idea that it is constant. That's pretty important in knowing this. So how do we determine things in this particular type? We could also determine the change in the displacement, which is from our chapter 2 topic in linear motion. So we have the velocity along the horizontal times the time. Since a while ago we take note that the component of the horizontal velocity is equal to v cosine theta, we can plug that in here. So we have that, or we can rearrange this to find for the final distance. So we also take note that this is also equal to the final horizontal velocity. We can also find the change in the height of the object in type A by using the previous linear motion equation. The second type of projectile motion is object or are objects thrown at an angle. So we can see here in the diagram how the motion diagrams are shown in terms of the components of the velocities on the x and the y. So you would notice that when the object reaches its maximum height, the velocity y becomes 0, but then there's still the horizontal velocity. You would also notice that the horizontal velocity here stays constant. So objects that are thrown at an angle is going to give us a combination for the velocities. So velocities are a combination of constant horizontal velocity. And if we look at the y, we'll see that the vector is getting shorter. So what can we tell about that? That as it goes up, the velocity changes. So you have an initial velocity in here. So technically it's almost similar with the type A, wherein we have the objects thrown horizontally, except that we now have the magnitude for the initial velocity on the y. And you would notice here, as it passes this point, the vertical velocity changes. It now increases its magnitude here. So it's the opposite on this particular part. So this part of the parabola. So we can now say that it is also the changing vertical velocity. So we can use to find the range, the total distance in the horizontal, so that's usually referred to as the range. We could get that in terms of the velocity on the x cosine theta times time, or we could rewrite it if initial distance is given. So we have cosine theta times time, and then we can also determine its maximum height at this particular point. So sometimes we've just written down as h max, or the y, which is equal to initial velocity on the y minus 1/2, since gravity acts on it, and we have gt squared. And we can also plug in this case, we can plug in the component. So we now have v y sine theta times t 1/2 gt squared. So that's our working equation to find the maximum height, the y, and then this one to find the range. We can find the velocities as well. So we have the velocities on the x cosine theta, and then we have the velocities on the y v sine theta. So let's apply some of the information that we have based from your readings from this short lecture. So let's solve problems along the projectile launch horizontally. And for B, let's use page 116 of your book, question number 63 for projectile launch at an angle. We are going to solve this in the classroom.